This is a life-size model, so the one at the back is the soft X-ray imager, which we call the SXI. And SXI will enable us to take a picture and measure in semi-real time the position of the Earth's magnetic boundary as it moves against solar wind pressure.
Yeah, this is only one of the instruments mounted on the spacecraft.
Yes, there are 4 instruments in total.
I can see that our instruments will be here on top.
Yes, so this is a model of the spacecraft. And so the SXI is at the top. The little one next to it is an ultraviolet imager, and that will look at the northern aurora at the same time the SXI is doing its observations. There's also a magnetometer to measure the local magnetic field, obviously, and a light ion analyzer to measure charged particle densities.
So, correct me if I'm wrong, my understanding is this spacecraft with the 4 instruments mounting on top will help us understand or give us a well-rounded picture of the magnetosphere.
Yes. We're doing it now because we've developed a new way of actually studying this. So, in the past, people built spacecrafts which flew around, and they contained instruments which can measure magnetic fields and plasmas and things like that. And they would fly around and they would detect those properties of the Earth's magnetic field at the particular points at which those spacecraft were. We're doing something new. We're taking pictures, we're taking images to essentially detect where the Earth's boundary, so the region of space between where the Earth's magnetic field dominates and the solar wind dominates. And we can take a picture and make a movie of how that boundary changes. It's quite dynamic. It's the pressure moves a lot, and so the actual boundary moves back and forth a lot.
So can I say, in comparison, in the past, we could only detect some of the points in the boundary, and now we are looking at a well-rounded picture of this magnetosphere of Earth.
Yes.
And also it's because, as you said, it changes all the time. We want to know what the dynamic is like, how it changes.
Yeah, so before, if the boundary changed but your spacecraft wasn't there, you wouldn't have known that. But because the orbit of SMILE allows long observation periods up to about 40 hours. It has about a 2-day orbit, but about 40 hours of that is available for science. And so we can track that movement continuously for that sort of period of time.
Do we know how long it would take us to map out the whole magnetosphere?
We will be in operations initially for 3 years, and then the spacecraft itself, the mission will last up to 7 years. So we will get a lot of data accumulated. But at any given time, although the field of view is quite relatively wide, we get a small part of that. But certainly over a period of weeks and months and a year or so, we can develop almost like a 3-dimensional global picture.
For many of the viewers, the audiences, I think they are wondering what real-world impact does this mission have?
Immediately, what economic impact there is the fact that there's this high-energy particle stream from the sun creates something called space weather. A lot of our modern technological world depends upon spacecraft, communications and so forth. And the radiation caused by the space weather can damage satellites in space. So economically, if we improve our models of how the system is reacting, then we can perhaps mitigate the effects of space weather in the actual future. Although SMILE itself is it's not predictive. It wouldn't tell us immediately there's something needs to be done because we have to download the data, analyze it, and so forth. So I think the area of space weather is and it is a very large economic. There are hundreds of millions of billions of dollars invested in space instrumentation, which could be effective.
Mm-hmm. And what are you expecting to find out? Do you have any hypotheses before this mission?
So we want to measure, for example, this changing boundary on minute timescales. So in order to prove that, or at least demonstrate that it is possible, you have to have an idea of the capabilities of your instrument and the strength of the signal that you're trying to observe. And so you do your simulations, you put those things together and say, yes, if our instrument works as expected and if the signal strength is what we expect, then we can detect this boundary movement on minute timescales.
So this is the first time that Europe and China are working together at such level. I know you build this mission from ground up all together. The teams on both sides are expected to analyze and collect all of the data together at the same time. What significance is this collaboration?
The significance is that it proves that the world's scientific community can work together in a completely open fashion. All of the data from all of the instruments go public at about the same time, and so the entire world's community can access that data. It's freely available. I think the significance of being able to work together in such an open fashion is very important.